Hello everyone, today we are going to perform CFD analysis of drone propeller. So now during the simulation we will be covering these 5 following things that has mentioned. So now for this I am taking fluid flow fluent. Now take geometry, import geometry, edit and design modeler. Now click on generate. Now we have a propeller. First change units to centimeter. Let me just find the length of this propeller. Which is 5.5 centimeter, and I would like this propeller to be 28 centimeters. So we'll use scale, apply. Now scaling would be if I click generate. Now this is 28 centimeters. Now again apply, apply. This is 28 centimeters. Okay, now we have propeller. So let me just fill this area using fill option and click on generate. Now we have two bodies. I'll just merge this body, select apply, select all body, two body, click on generate. You have a single body propeller. Now create enclosure, setting cylinder on z-axis, radius let me just say 1 centimeter, point 5. Let's just generate and see how it looks. Okay, 0.5, generate. Okay, now we're gonna name this as rotate. Okay, now let's create another one, another enclosure box. Let me say 42, 70, 42, 140 and click on generate. Okay, this one looks good. Now we are going to separate. Let me just name this as static body. Okay, so let me just first remove this rotate from the static as well as remove the propeller from the rotate domain. For that we'll need to take boolean, select subtract, rotate, select rotate, propeller, preserve tool. No, I don't want to preserve propeller. Select OK, generate. Now we are left with two bodies. Propeller is removed. Now we'll do the same thing for this. First select the static, then apply rotate, preserve the body, yes, generate. Now we have two bodies with propeller impression on rotate domain. Now let me just use symmetry option to cut the model in half. It's YZ plane. Select YZ plane, apply, generate. Now we have left with the half model. You can see the half propeller. Okay, now we need to create for this rotate domain. We need to create two surfaces at this plane, or two faces. This is single face, this is single face, rotate single face. Now we need to cut this into two so that we can give periodic boundary condition to this rotate domain. So I'll go to for that, click and sketching, draw a line, simply draw a line, just take a line, vertical line. Okay, now I'll give symmetry conditions so that this line is exactly at the middle of this rotate domain. So I'll symmetry, this line, this edge and this edge, so it is exactly at a symmetry. Now I'll just go to modeling, concept, line from sketch, apply the sketch, generate. Now we have this line. Okay, now let's create face split, apply this face, apply this edge filter, apply this one. Now generate. Now you'll end up with two faces. Yes, two faces. And you can also check for the this distance. So, analysis, distance finder. First let me just click to edge filter, this edge and this edge. It is 14.538. okay, same 14.538, so it is similar. Now I'll just suppress this one. So now we have two faces for this one, so with using this face will give periodic boundary condition. So now we are in the mesh. So under geometry we have rotate, static. Inside the rotate we have propeller. We have propeller. Okay, so the mesh, go to method, apply, select all geometry, set this to tetrahedral. So without doing this patch conforming method and setting method to tetrahedral, you won't be able to convert the mesh into polyhedral. So to get a polyhedral mesh you need to do this step. This is the mandatory step. So now we can perform the remaining. Let's go to sizing, hide body, take this body, let's go with 6. Now again hide the surfaces, select hide face, now give another sizing. This is for the propeller, select box, see the only propeller is selected. So apply 6 faces. Okay, I'll give this around 4. Let's see for okay. Now default is set to 12 centimeter. Okay, let's just see how that turns out. Change it to mm, sorry, change it to m, and this would be 6, this would be 4, or change it to 3. This is 123 mm, so somewhere between 50 would be great. Mesh look good. Now okay, reduce to 4, let's go to 2, check under statistic nodes. Okay, generate mesh, okay, I think this one would be okay to 5, generate mesh. And this default 50 mm mesh sizing is for the static body. Okay, now let me go to name selection, so this one I'll name it as propeller, show all faces, show all body. You can see the outer mesh. So we can reduce this one, it's a little more, little bit of okay. So now we have propeller, to single select this one, I'll name it as symmetric. symmetry. This one I'll name it as periodic 1. Periodic 1. Okay. And the remaining one is periodic 2, the other face. So now generally we would give the name selection. The top one obviously the inlet, the bottom one would be the outlet, and this all three remaining three faces would be wall. So the airflow will be from the inlet region, but we would not going to do that. Instead I'm going to name all the surfaces, outer surface of all the outer surface of static body as outlet. So this approach would give us much more realistic to what we would have done in the physical, using same propeller in the physical environment. So which means I have named the outlet, so every outer face of the body is set to outlet, which means it is connected to atmosphere. With this we don't have to give inlet velocity at the inlet, so it just much more realistic approach. So I'm just trying this out, this one. You can also try the top surface or face as a inlet, the bottom face as a outlet, and remaining 3 1 2 3 sides as wall. So which in that method also we have done that video. I'll put the video link in the description and comment section. So now we are all set. Okay, let's just update. Okay, now come to setup. Double precision parallel to okay. Now if you look at the mesh, it is a tetrahedral, not a polyhedral. To make a polyhedral mesh, make polyhedral. Now it's done. Just close the Fluent. Now we are going to again launch the Fluent. Now we have polyhedral mesh. Just look at let's have a look at propeller display. You can see polyhedral mesh. Okay, so we are using steady state simulation, gravity, x direction in the x axis. So now we go to model, set viscous model from laminar to turbulence, k epsilon, realizable scalable wall function. Okay, now under material, for fluid it is air, for solid I'm changing plastic ABS. ABS, and its density is, to find out the density we'll use engineering data. Go to engineering data, click on engineering data resource, general material, sorry, no, granted. Here we have ABS plastic. Click ABS plastic. Its density is 1040 kg per meter cube. So 1040, I'll set to 1040 kg per meter cube. So I'll set to change. Okay, now we have used plastic ABS. So now under cell zone condition, rotate, edit, air, material is air, frame motion, about Z axis, changing units from radians per second to RPM, angular velocity change to RPM. Okay, close. Now we have RPM, so it is minus 8000 RPM. Actually 8000 RPM. Negative indicates negative because this propeller is counterclockwise propeller is a counterclockwise propeller. So in order to get thrust in the negative Z direction, we have to rotate it in the counterclockwise direction. So this minus, make sure it the RPM rotation is in the counterclockwise direction. So that's it. Hit OK. Now under operating condition, that now under boundary condition. So as I've already told you, we do not have any inlet surface. We converted every outer surface to outlet, which means every outer surface is connected to atmosphere. So we don't have any inlet, so we don't need to give any inlet parameter. Here we have a periodic 1 and periodic 2 is a wall, but we need to change it to interface. Then only we can give periodic boundary condition using this interface. Set to interface. Okay, now that's outlet, that's supposed to be connected to 0 gauge paper, which means 1 atmospheric pressure. So yeah, so now the whatever the thrust will be generated, it will be, the air will be coming in from all the direction. So let's just see how it turns out in the simulation. So now under mesh interface, now you see unassigned interface zone, periodic 1, periodic 2. With this we will create boundary condition, periodic boundary condition. Okay, set, I'll just set it to PBC, periodic boundary condition. Set periodic 1 from interface zone 1 and take periodic 2. You can take periodic 2 here and periodic 1, whatever. So set to rotational, auto compute offset, and take it 180 is the angle. Created it, now close. Now we have PBC, boundary condition PBC. Okay, now let's go to report definition. I'll create report for thrust. So force for propeller, so this is the thrust, 0 on the Z axis we want. Sorry, it's print. Set to OK, thrust. OK, close. Now monitor, I'll change the residual from default 10 to the power of -3 to 1e -5. Copy, set it to every parameter. Okay, now let's hit go to initialization, hybrid initialization. Okay, hybrid initialization is done. So now under run calculation, I'll say 1000 iterations. Hopefully it will take lesser than 1000 iterations, so set calculate. So this is our force graph and this is our residual. See, our thrust force is not changing, so it's stabilized. So at this point we can stop our simulation, but since this residual is dropping, we're gonna see it 500 iteration and we're gonna stop it at 500 iteration because the force is not changing. So it doesn't matter if I'm going to iterate for one more 1000 iterations, the force will be linear, the constant from this point. So I'll just stop the iteration. Calculation is complete. Okay, so you can see the residual was also wasn't changing that much. Okay, you can see the force. What is the thrust? Click on force for propeller at Z 0 unit force. If you say print, okay, propeller print. Now you can see pressure in -5, which means 5 newtons, almost 6 newtons of thrust is generated in the negative Z direction. So I'm going to close the Fluent. Since we have stopped our calculation, I'll just say accept interrupted solution as up to date. Okay, now let's go see results. Let's just first see the vector. As you can see, the vector see the particle is coming from all the surfaces. Okay, we can also look the streamline. So streamline, now you can see streamline over a static body, the outer surface, using 100 maximum points, and it's forward. So you can see it's air particles is coming from all the direction, mostly from top, and this is the thrust. So let's just give counter. Okay, stop the streamline. You can see that's the pressure on the propeller. So now we can also animate using the streamline. Slow options. Okay, okay, play this. That's ball coming from all the surroundings. You can also look at using more streamlined values. Okay, 250. Now, so this is the complete CFD analysis of drone propeller using half geometry with along with periodic boundary condition and without using any inlet velocity. So no inlet velocity was present in this simulation. Well, if you wanted to see the simulation with inlet velocity with full geometry, you can check out the video. Link is in the description. I'll put it one in the comment section as well. The video I'm referring to is full geometry without periodic boundary condition, and we used inlet velocity. So thank you.